Okay, so good morning to everybody. First of all, my name is José Capmany. I am at the Technical University of Valencia and also a co-founder of iPronics. I would like to thank, of course, ALTER and UPM for inviting me to deliver this speech. This is going to be a little bit different from what I do usually. This is more like a lecture than actually a very technical presentation on the work that I'm doing, but I think it's also a good opportunity to give some kind of basics, especially given time you're going to be interested in working in the field. At least you know you are introduced to the basics. So I don't have much time. Usually a course of this will take like 4 hours, something like that. So I have to compress it in less than 40 minutes. So I'm going to try to do my best. And this means that I will not be able to cover everything. There are not many equations. I just stick to the very essential ones. You don't have to follow them. It's just to provide you with the backup. You will have the view graphs if you want to later, if you want to have a more detailed browsing of them. So as for now, just try to relax and see if you can grasp as much concepts as possible. Right, so let's start. I don't know if this. Oh, okay, right. That's the index of my talk today. Okay, so I'm going to provide an introduction to what do we mean about when we talk about microwave photonics. And one of the key central parts of the microwave photonic system is actually the link. The link can range from very simple configuration to a very complex one. So I'm going to try to embrace all of them in describing what I call a basic configuration of that link. And then I will go to review on the basic devices that we have for MWP systems, what we call the toolbox. What are the different tools that we have to implement that usually come from standard photonic components. One of the things we don't want to do in microwave photonics is to require specialized components, because that means that it will be we will not benefit from economies of scale, and therefore systems can be very expensive. So then I will cover a little bit of transmission techniques. What we use, what techniques do we use to transmit signals from a central station to a remote antenna? And finally, and probably this is the most technical part, I will speak about the performance metrics and the figures of merit. This is interesting because at some time, if you work on that, you will going to see that you need, and you read papers, you will be consistently referred to 3 or 4 different figures of merit. So it's good to understand them and what we mean by them. I will try not to be very detailed on that. As I said before, you'll have the view graph, so no problem. You can always consult that. All right, so let's start and provide an introduction to microwave photonics. So microwave photonics is like cross-border discipline that brings together both worlds, as it's been said just a few minutes before. And it's been around like 40 years right now. And it is true to say that initially it lacked commercial applications. So the main interest was to apply them to defense applications, right? Because this where the enough budget was to, let's say, fund the research on these, in principle, specialized systems. But right now, this has already changed a lot, and MWP embraces a lot of civil applications. Okay, and of course, one that is very representative is cellular communications, but there are other more which are listed here. You can have several examples. Right. So let's see, what do we mean by microwave photonics? We work with standard radio frequency components. You usually get a signal that comes from whatever generator. You may be a specific generator, or you are getting your signal from an antenna or from an array of antennas. And you have your signal at a given portion of given part of the RF spectrum. What you want to do with it is to process in a way, so you use filters, delay lines, or whatever, and hopefully you're able to process your sidebands, your information, and then either you detect or you irradiate whatever the application is. In microwave photonics, what we try to do is to substitute this central part. Okay, that's the traditional RF operation. So what we do in microwave photonics is get rid of this central part and actually use photonics for this intermediate part. So what we do is just feed the signal into up-convert into the optical domain by using usually the main solution is to take an optical modulator, external modulator, which is fed by this RF signal on one side and a continuous wave optical signal on the other. What you do basically is up-convert. If you're lucky enough to have a linear modulator, you will do precise conversion, up-conversion. Then you send it through an optical core, which can be an optical fiber subsystem or more recently an integrated photonic chip. And you do your processing and then you down-convert in the photodetector and actually you are ready to re-radiate or detect your signal. Well, why do we use the optical core? We use the optical core because photonics is low loss, is almost frequency dependent low loss. It's controllable if you use optical chips, and it's reconfigurable. So you might send the control signal to your chip, and you may actually change your processing capabilities in the up-converted domain, optical domain, and hopefully change your RF signal when you down-convert. So that's the main idea. Broadband immunity to broadband operation, immunity to interference, and of course low losses. Right. So we can use this very basic configuration, which I will detail a little bit later, to do to carry out a lot of functionalities. I listed some of them here. They are not all of them. This is not exhaustive list, but it actually, I would say, it includes a good number of them, and some of them are very well known, like filtering or beamforming, very popular, and probably less well known is the analog to digital conversion that we can use, for which we can use these systems as well. But these are the main, let's say, basic functionalities upon which we can build elaborate systems. Right. So applications, well, there are many, as I said before. Right now, civil applications are probably the most is a wider number of civil applications than defense, by the way. But of course, can include like 5G, as I said, 5G, satellite communications, medical imaging systems, more recently fiber sensors, sensing devices, sensing configurations, wireless sensors, etc. So the key point is that there is a translation here from a wireless world to a wired segment of the communication network, and this usually takes part in a base station. Okay, so this is where the transition is made, and where usually we host most of our microwave photonic systems. Not in all occasions, but most of them. The main equipment is there. Right. So let's see what is the basic configuration of a microwave photonic link. We have, in a way, anticipated it before, but we are going to stick to the photonics part. As like I said, it's a particular part of a particular version of a communication system. So we're going to have a transmitter, you're going to have a channel, and you're going to have a receiver. But in this case, like I mentioned before, there is a transition at the transceiver, the transmitter and the receiver from the RF to the optical world, and vice versa. And in the middle, there is a photonic core. We don't want to be very specific about this, so it's usually I will use this terminology that we have here to label the RF input power, the RF output power with capital letters, the intermediate optical powers with lowercase letters, and photonic core action, whatever it is, I'm gonna represent it with transfer function, whatever it is. We don't care about that. All right. So these are the three main parts. So what do we use to implement all these parts? What kind of devices do we use? Okay, right. So let's say I take a very simple example. I change this, I substitute this very complex transfer function by just a single fiber link. Okay, just for illustration purposes. So we have different options in the source. We can either use the direct modulation of a laser, or we can use an external modulation, okay, which is the most common option, because doing direct modulation to a laser is bandwidth limited, and you have also you produce deleterious effects which you cannot get rid of, like chirp and nonlinear operation. And in detection, either we use direct or coherent detection. Right now, the most popular options are to use direct detection in the detection part, and external modulation in the transmitter. This is the most common solutions. So for the transmitters, there's a wide range of elements that we can use, from the most let's say more standard fabric parallel lasers to single line with DFB lasers, vertical cavities. These options, each one has a different possibilities or different characteristics. But if you want to go really high in the frequency, the real option is a DFB laser if you really want to do direct modulation. Otherwise, you're going to use it in continuous operations, so you don't care anything about the modulation bandwidth. What you really want is the laser or the source to give you enough optical power. This is going to be a very important parameter, as I will show later. For the modulation device, we usually employ Mach-Zehnder modulators. These are integrated devices which are really a balanced interferometer. Right now, there are many options. Right now, lithium niobate modulators are the most employed alternative, because they provide different advantages, in particular high modulation bandwidth, and also it's quite flexible, because this is a very simple standard modulator, but you can use what we call dual parallel modulators, whereby you can use you can generate in quadrature and in phase and quadrature signals for complex modulation formats. These are broadband, like I said, but these are not the only option. You can use other alternatives. We can either use electro-optic polymer modulators, which are very broadband. Standard integrated Mach-Zehnder modulators have a modulation bandwidth around 40 to 60 gigahertz maximum, more or less. There are exceptions, but with polymers you can reach and exceed 100 gigahertz. Although they are very difficult to operate, and they are very sensitive to input optical power. So the standard one is right now is the Mach-Zehnder modulator, and we still have a third option, which is to use an electroabsorption. But this is not what we call an electrorefractive modulator. This modulator works by changing the absorption rather than the refractive index or the phase. So it's inherently very nonlinear, and this is the last thing you want from a modulator. You want, in analog applications, you want a very, very linear modulator. So with the Mach-Zehnder, you can choose your bias point and actually get a quite reasonable linear operation. Okay. Finally, regarding the transmitter, I will show you different ways in which we can operate the modulator. The modulator usually has two electrodes where we feed the RF signal, and we have another separate terminal where we do the biasing. That's the DC voltage. And depending on the configuration and the phase shift that we apply to the modulator, then we can get different operation regimes. We can actually obtain double sideband modulation, single sideband, which is very important for to combat chromatic dispersion, and we can have also double sideband modulation with suppressed carrier. We want this, for example, when we this last option, we want to generate high frequency RF signals from standard modulation. But for transmission, the option that is based on single sideband is probably the most attractive one. We just use it to suppress either the upper or the lower sideband, and with that, when we avoid the destructive interference that arises in the signal bit in the photodetector, and therefore we can have systems that are immune to dispersion. Okay, finally, for modulators, for detectors, okay, we need high bandwidth, high conversion efficiency, and what is very important also, very high linearity. The detectors have to withstand a very high dynamic range and still operate linearly and not produce extra intermodulation. So we have two options: the typical thin photodiode, which is the most employed solution right now, and we could also use avalanche photodiodes, but this is not so interesting because we don't get really much advantage on that. We want higher power. We will use optical amplifiers in our links. So, but PIN can actually be. You can always think in different structures whereby by feeding the light in different parts of the photodiode or with different schemes, you can gain you can reduce the capacity and then therefore increase your bandwidth, your detection bandwidth. You can use lamped or distributed applications. And right now, the most interesting option is to use the traveling wave photodetector, where if you are able to match the velocity of light propagation and the velocity of the RF signal that you're generating, you have maximum bandwidth. And furthermore, if you restrict the operation to only one type of carrier, we call it UTC device, then you suppress long delay times from half of the carriers, and then your bandwidth is expanded. Okay, we can use, of course, more components. And it is typical to use optical fiber links to connect the transmitter. And you know that the fiber is dispersive, and this happens because when you are sending your signal through the optical link, you have your carrier and your sidebands. So in detection, each sideband fits with the carrier, and if you are not very careful, because of dispersion, the sidebands have different phase shifts, and it may happen that these two beatings are opposed in pi. So when it comes to the detector, you basically have a null. You don't have any signal. You have signal fading, and this is what you can see here. And sorry, these nulls correspond to different frequencies. So if you're transmitting a broadband signal and you occupy this portion, then your signal is going to be lost. And one way to combat this is to use the single-side modulation scheme that I mentioned before. Because in this case, you will not have a destructive interference because you will not have interference. Just the beating of one sideband and of the optical carrier is eliminated. Of course, you can use dispersion compensation techniques as well, and dispersion shifted fibers, etc. But the typical solution here is to use single-side modulation. Okay, so I think there's pretty few more to say about this. There are, of course, extra elements that you can use. You can use, instead of single mode fiber, you can use multi-mode fibers. There's been quite interesting experiments using those for short range applications. optical amplifiers, of course, chips, but we're not going to talk about chips in this here. Probably Guillermo will say something about that, about the integrated micro photonics, and optical amplifiers, multi-core optical fibers, etc. Gratings. The toolbox is quite big. Right. So let me devote a little bit of time to explain what are the transmission techniques that we use in microwave photonics. There are basically three options that we have. Okay, this is going to be very brief. The first option is what we call radio over fiber, pure radio over fiber. And here we, the way I'm going to explain this is by referring to a link between a central office, okay, and a base station. Could be other pair of end nodes, but just to put it, and we have like a fiber network. So when we do radio over fiber, we generate actually the optical signal in the central office, and what we do is we have our baseband signal. We upconvert to intermediate frequency. We use a local oscillator to convert it to the radio frequency, and then we modulate directly or externally our signal, and we transmit. And in the base station, we don't have basically to do anything. It is the photodiode or the receiver that is going to do all the conversion that is required, and therefore you can transmit on radio directly. So the base station is very simple. And all the complication goes into the central office, which is good because you want the expensive equipment to be in the central office, not on the base station. But on the other hand, then you will have high frequency signals going through the optical fiber link, and then you have to be careful about controlling dispersion effects. So one solution that has been used many years, not so much right now, is to take an intermediate solution, which is, let me go back a little bit. You remember this transfer function, okay? So let me try to go. I think I block this. No, doesn't want to go forward. Anyway, yeah. If I transmit on high frequencies, I may face the risk of falling here. So why not try to do the transmission a little bit lower, but still on the RF band? Okay, so that's the whole thing about this second option. What we do here is just upconvert to the intermediate frequency, transmit, and then in the base station we have to first of all bit recover the IF and then upconvert to in RF using the local oscillator. But this is not good because then your base station equipment complicates. And finally, this is probably the most widely used technique today, is to use baseband over fiber. Baseband over fiber is that you don't care about radio until you're at the very end. You actually do baseband transmission, that's bits, ones and zeros, and when you go into the base station, then you have to do IF plus local oscillation of conversion. So this ends up in a quite rather complicated and expensive, especially if you want to go to the millimeter band. It's okay if you want to go into the 3 gigahertz or whatever band, it's still economically feasible. But if you think that when you do the transition, if you want to evolve your systems to 28, 30, 60 gigahertz, then you're going to have a lot of base stations, even though they are smaller, and you don't want this solution. Okay, so that's finally leads me to the final part of my talk, the performance metrics. Okay, performance metrics what I have to say is that after all, if you see it from extreme to extreme, this is a microwave photonic system is like a microwave or a radio frequency system. So we are going to qualify them and use the same metrics as you use in an RF system. So actually, what we want at the end is to really reproduce the RF signal, the receiver, the best that we can after being processed, without any additions and without having a lot of losses and a lot of noise. So to do this, we use 3 different figures of merit. There are more, but the 3 main are the ones that I'm going to explain here. And I'm going to explain through this very simple diagram that I showed before. Okay, so just think that we have a very simple signal. We have a tone at a given radio frequency signal, and we want to transmit it through a system. And at the end, ideally, we would like to recover our tone, okay, as it is. Okay. One can say, well, that's a very simplistic assumption because you're basically doing nothing, okay? But this is for explanation purposes, okay? Let's say I want to do something with this tone, which I would do here, but right now this is going to be a simple link. So if I don't do anything and I try to recover and I see what I have at the output of the system, I will see that my tone has been reduced in amplitude, so there is a loss. When I didn't have a lot of noise here, I will have a considerable noise background here. And furthermore, I will see several nonlinear terms here. So these are the 3 things that I need to qualify with my figures of merit: loss, impact of nonlinearities, and noise. And these are the 3 metrics that I use: the link gain, the dynamic range, and the noise figure. So I'm going to try to explain a little bit how do we quantify them in RF photonic systems. Okay, don't get scared, okay? Right, so again, remember I provided these definitions, okay, a while ago, okay? So I really want to know what are these figures of merit. And what I want to know, first of all, is the gain, okay? So the only assumption I'm going to do here is that this photonic core, as I said before, is going to be a linear system. So when I have my input electric field here and my output electric field, they will be related linearly in the spectrum by a transfer function that takes into account the core and probably some effect of the detector. So actually, this is what I assume, but what I need is a relationship between the output power and the input power in the optical domain. This is not very difficult to compute, okay? At the end of the day, what you have is this relationship. And what this relationship tells me is that the output power is the input power multiplied by this strange factor. And this strange factor is nothing more than the beating between the carrier and the sidebands. Okay, so that's easy to understand. So this is the price I have to pay from going from the electric field to the optical power. Okay, right. So actually, I term this as a T function. Right. So if I want to calculate the RF gain, actually I need to calculate the output power versus the input power. The output RF power versus the input RF power. So I can do the math, and I will get that this is the multiplication of 3 factors. A first factor that takes into account what is the gain of my transmitter. An intermediate factor that is the effect of the channel, and a final factor that is the gain of my detection system. Okay, I can use this equation or use this more traditional logarithm version. So basically, this is what I get, and depending on if I'm using an external modulator or a direct detection or PIN diode, concentrated, distributed, these factors will change. But this is basically what we use. If I use a standard configuration with an optical modulator, there are different things that are important in these two factors, in this and this. In the transmitter, for example, I need to know what is my laser power. I need to know what is some technological parameters of my modulator, the VPI, for example, other things. If for the photo detector here, I need to know several parameters like the responsivity, etc. Okay, I'm not going to do a very provide more details, but what I'm going to put you is the expression of the gain for two different examples here that are very representative of practical systems. This is external links using external modulators, okay, and either dual double sideband or single sideband. You will see here, this is the factor of the channel, which in one case it has the two beating terms. When you have single side modulation, one of these sidebands disappears, so that's more simple. And here, what you have here is the different parameters from the detector and the transmitter. So very important is the power that the laser delivers, and that is why I said that we always would like to have a very powerful laser. This is the responsivity of the photodiode, and this is what we call the VPI voltage of the modulator. As you may understand, for having high gains, we want this to be as small as possible and this as high as possible. But the other things are parameters from the electric circuits. Important is that there are in practical links, usually gain is below 1. So why calling it gain? It's a tradition. Okay, it's really lost, and it can be very high. The standard values range in between -20 or 25 to -10. Okay, if you only use passives. Okay, and this is because usually this is lossy, but the channel is not so lossy, but the slope efficiencies of the transmitter and the detectors are usually lower than 1. Okay, due to energy conservation. But there are three mechanisms to reduce losses. First of all, we can always trade excess bandwidth for reduced loss. And this means that instead of aiming for broadband links, if you're able or you are prepared to work with lower bandwidth links, then you can increase your gain. Of course, you can change the characteristics of your modulators, and you will hear very frequently that everybody is quite mad at trying to find low VPI modulators. And the reason why is this, because it's on the denominator, or use high power lasers. And finally, there's an obvious solution that is to use optical amplifiers. If you use an optical amplifier, then this factor is multiplied by the gain of your amplifier. With amplifiers, you can have really RF gains. That means over 0 and as high as 10 dB. Right. So dynamic range. When you use in your microwave photonic link, you usually use a voltage RF signal as an input, and you have an output current signal, and you want to have an expression that relates the output variable current in terms of your input variable voltage. Okay. Usually, the way that you will find this in the textbooks is to lump all this the action of all this link into a function, whatever, okay? And this function is expanded into Taylor series. I don't know if you still remember the Taylor series expansion, but it's something like that, okay? You use you are basically assuming that this H function takes your input voltage and transforms that into your output current. And of course, you are always free to do this Taylor expansion. Now, the nice thing about this is that this output current is expressed in terms of your linear input voltage, but also you have higher order terms, and this is where intermodulation and distortion comes, and dynamic distortion comes. Okay, so just think again that we go to a very simple example. A very simple example is to come here and say, okay, my input signal is going to be a humble sinusoid. Okay. And let's see what happens if I substitute this into this monster equation. Okay, if you do that, first of all, you have to compute your powers of your voltage, and you will see that as you increase the power, then things start to get complicated. You start to have harmonics. You start to have a higher order harmonics, etc. So that's bad news, because it means that if you use the Taylor expansion, actually what is going to happen is that it's going to give you as a result harmonic distortion terms, non-linearities, to put it in a way. Okay, so actually the output current can be very complicated. This is actually what you would like to have, an amplitude and only a term in omega, but it turns out that you have harmonic distortion terms. Okay. Second order, third order, and if you average that on your detector, okay, what you will find out is that you have different powers for the different terms. But if you express that on logarithm units, then you end up with equations of straight lines, where the independent variable is the source, the RF source power, and the independent and the dependent is the output power of each of these harmonics. And you see that these are all straight lines, but the slope is increasing by 1 unit. And this is what we use to represent. If instead of one signal you have two tones, then the thing complicates, and apart from harmonic distortion, you start to have intermodulation products, but the concept is more or less. So at the end of the day, when you represent your nonlinearities, you end up with something like that. And this is what you will see in all papers. Every paper that revises MWP system will have a graphic representation, experimental representation, something like that, which is very similar to this. You will have the fundamental, this is the linear response of your system, which has a slope 1. And then you have different other contributions. So your usable margin is that which is comprised between the point where your signal is above the noise floor, and is still you don't have, and the noise floor is still the dominant degradation source. So you see, for example, if you have a system with that like this, then the first limitation comes from the second order distortion. Okay, so you can use your link. You can expect to increase your signal to noise ratio by increasing your power until you reach this point. In this point, what happens is that the intermodulation is going to dominate the noise floor. So even if you increase your signal power, your overall signal to noise ratio is going to degrade. In most practical systems, second order intermodulation is not very significant, because you will have all your channels inside one octave. So all your relevant intermodulation is going to be in the inside is going to be due to third order intermodulation. So this is basically the things that we have to learn about this dynamic range. Okay, so like I said before, at the end, I'm going to take just 1 minute, a couple of minutes more. Excuse me. No. Okay. So when the fundamental, the slope 1 output is less than the noise, then you have no signal. Then when it's bigger than the noise, you will increase your signal to noise ratio as long as you don't reach the point where the nonlinear distortion becomes more significant than your noise floor. Okay, so I showed you. Let me try to go very simple, very fastly. These slopes that you show here. Let me put it. The curve here. Okay. These have slope 1, slope 2, and slope 3. Okay. So really your usable margin, okay, will be this part. This is the range of power if you are limited by second order intermodulation or distortion. If you're limited by third order, this will be your usable margin. Okay, so this is the signal, your signal to noise ratio, your available signal or available power range that you can use. And usually we call those areas the dynamic range. Okay, and we define them for 1 Hz of bandwidth. So basically what you will see in the literature is that this separation between the second order distortion and the fundamental is usually measured in dB per a square root of Hertz, while when it is a third order, this is dB per Hertz to 2/3, and the typical values are these that I show here. This is what you will find in the standard. Okay, so finally and very fast, I'm not going to develop a little bit more on that. Is noise figure is like any kind of system. You have a signal to noise ratio here, okay, at the input, and a signal to noise ratio at the output, and the noise figure is the logarithm of the coefficient. But because we already know that P out divided by P in is the link gain. If we know the link gain, then we only need to know what is the input noise at the system's entrance, which is usually thermal, and the output noise. So it then turns out that that a very basic way to categorize this noise is to just only you have to take into account the output noise level, your link gain, and this is a quantity that stems from the fact that you assume that your input signal is going to be at 298 Kelvin. So just to give you a grasp of this, N out is usually around minus 140, okay, dBm. G, as we said, is, let's say, minus 10. So that makes minus 130. So this sum to 134 is plus 24 dB of noise figure. Usually the noise figures range from 10 to 20 something dB. Okay, so that's the end. If you want to know more, there are books, of course, a lot of books. If you are coming to the next OFC, I will be giving a 4-hour course, so you can see that going there. So thank you very much for your attention, and excuse me for going 5 minutes over the time.